Welcome to lecture 2 of vehicle propulsion systems. Last lecture we talked about the big scale and where this course fits in the society as whole, while this lecture goes into the analytical tools that we will use to analyze the fuel consumption of vehicles in driving missions. In this lecture you will get the first tools that you will use in the hand-in assignments and that you later will use for understanding different types of powertrains. Jumping into it, we will start with a repetition, then we'll go into energy consumption of a driving mission, and we will work on the analytical tools, and then we'll go into energy demand of vehicles and do a sensitivity analysis to see what components are most important when we design vehicles, if we want to design them towards low fuel economy. Then we'll look at forward and inverse modeling. And the inverse modeling, I hope, will be an eye-opener for you and give you a new tool for analyzing engineering systems in the future. We will also talk about engine models and put things together there so that you can get more tools to analyze the total fuel economy. A bit of repetition before we enter the main subject of today. Last lecture we talked about the energy system from primary sources, and then we looked at different options for energy storage, and we looked at the powertrain energy conversion, and we discussed the cut at the wheels, and we talked about driving missions. We also talked a little bit about the backcasting. So we look at what we have down here, and then we can propagate up. We can get numbers for how or low CO2 will be for different design options that we're making. Now we'll go to the energy consumption of a driving mission. For the future analysis, we will look at the cut at the wheels. So we will look at what does a vehicle require from the driving cycle. And when we make this cut at the wheels, we're not thinking about how the vehicle is configured internally. We're not thinking about whether we're using an electric machine or whether we're using a combustion engine to propel the vehicle. So the cut at the wheel will be important for the analysis to come, but before that I just remind you about our backcasting that we did. We work with the driving profile down here, and then we're backcasting the results to see what CO2 factors we'll have. So we can look at the energy driving mission and then the different options inside the vehicle and at energy carriers, and then we can propagate it up either to the traditional diesel and gasoline or natural gas or coal-based electricity, for example. Or we can go up at the renewables here, which is what we want to have in the desirable long-term future. Next, we'll go into the energy consumption of a mission, and we'll remember the cut at the wheels. So when we look at this, we'll work with the cut at the wheels, and we'll ask how large force is required at the wheels for driving the vehicle in a mission. Before developing the tools, we repeat a little bit of the physics, and especially the relation between work, power, and Newton's law. Here we're looking at the translation system, where we have the work that the translational system has is a result of the force that we integrate over the distance. We have work here, then we have another component which is power, and the power is the time derivative of the work that we're taking out. And if you look at the translational system, the power that is transmitted at the wheels is the force times the velocity of the vehicle. For a rotating system that we have inside the vehicle, for example, the part where we have the work, and the work is then an integral of the torque over the angle that we are pulling the torque. As for the translational system, the rotational system also has a power, work, and torque relation. So the power is the torque times the angular velocity, and we see that the force and torque have the same relations, and velocity and angular velocity have the same relations. When we look at acceleration of vehicles, we use Newton's second law to see how much force is required. For the translational system, we have mass times the acceleration, which is the result of the force imbalance, the driving and load forces. If they are in balance, so the driving force is bigger, then we get an acceleration. If the loading force is bigger, then we get a deceleration. We have the same relation for rotational system, where the torque takes up the same form as the force. So we have an imbalance of the torque will result in accelerations or decelerations in the angular velocity. Putting this into a vehicle perspective, we can look at the vehicle, where we have different forces acting on the vehicle, and depending on how these forces balance each other, we will get an acceleration or a deceleration, and it's the vehicle mass that tells how much this acceleration will be depending on the force imbalance. We have the tractive force. The tractive force is the force that pulls the vehicle forward. In this case, we have a front wheel driven vehicle where the front wheel is pulling the vehicle forward. Then we have rolling resistance that comes from the wheels. We have air drag, and we have a disturbance force acting here. And we also have the gravitational force that in this case opposes the movement uphill. We should comment that the gravitational force is not a loss force, it's storage of potential energy. But when we're going uphill, we need to overcome the gravitation to pull the vehicle uphill. But we get that back when we go downhill later. We will look at these components in the next step. So we'll look at air drag, we'll look at rolling resistance, and we'll look at the gravitational force components. Air drag, you should recognize the formula from the basic high school physics, where we have 1/2 times the density of the air times the cross section of the body times a drag coefficient, and the drag coefficient is related to how well the vehicle is designed with respect to streamlines over the body, and then we have the velocity squared. Approximate contributions to this air drag is that 65% comes from the car body, we have 20% from wheel housings, about 10% from exterior mirrors, eave gutters, windows housing, antennas, etc., and about 5% from engine ventilation. Next component is rolling resistance. So the rolling resistance depends on the load and tire road conditions. If the vehicle is more heavy loaded, we will get more deformation of the tires, and it's this deformation of the tires that gives rise to the rolling resistance. So the behavior of this rolling resistance is like this, where we have a speed dependent behavior. So the rolling resistance coefficient is here on the y-axis, and these are for different points, so an average point and a minimum point. Standing in a nominal point here, we can influence the rolling resistance. For example, if we deflate the tire, so we take air out of it, we will get more deformation, which will result in higher rolling losses. And we can overpump it, or we can increase the pressure, then we can decrease the rolling resistance. Or we can influence, if we go faster, we will get an increase in the rolling resistance too, or if we decrease the speed, we will also get down here. You can see that the temperature varies with the tire, and you can see that it's low here and it's high up here. So when we increase the speed, tires will heat up, and this heat is a result of the losses that are generated in the tire. The velocity for normal driving, we have a fairly flat curve here, so not much is happening. And the velocity has a fairly small influence for normal driving, where we have low speeds. Then it starts to increase rapidly when we go up to higher speeds and when we go up to the limitations of the tires. Different tires have different maximum velocities. For example, winter tires have lower maximum velocity than summer tires have, due to that they have softer rubber in the material. The assumption that we find in the book is that due to that we have flat here and that we're spending most of the time in low velocities, they make the assumption that the rolling resistance coefficient is constant. But we should remember that this is an assumption. Just so that you will remember this effect here and why you should avoid using the incorrect tires for your vehicle. To describe this so that you will remember it, I will use the anecdote of Bugatti Veyron. In the advertisement material it says that if you drive the vehicle at maximum speed, the tires will last for 15 minutes. But that's okay, because the fuel tank gets empty in 12 minutes, so there's a safety margin. Hopefully this anecdote will help you to remember this part here, where we start to increase the amount of energy that we put inside the tire that heats it up and can get it to explode. The third component is the gravitational force, which is a loading force that we can feel on the vehicle. It is not a loss if we look at it over a driving mission, because we're storing potential energy when we go uphill that we later can recover when we go downhill. If we look at it from a driving perspective, while we're driving right here, right now, we will feel it as either an opposing force or a helping force. And that one is modeled like this, so we have the gravitational force, the mass of the vehicle, times the gravitational constant, times sinus for the slope. In the book, flat road is assumed, and we will mostly work also with flat roads in the hand-in exercises. There is one special extra hand-in task that relates to a truck, where you can look at the influence of gravitational forces on the optimal driving schedule. The final component that we can look at in the acceleration part is the inertial forces. So for example, inside the driveline we have the wheel, we have the driveline coming in here with the gearbox, and then the engine. The engine has an inertia and the wheel has also an inertia. Putting these together, assuming that the shafts are rigid so that when the wheel rotates, the engine also rotates with a ratio determined by the gear ratio. When we work with the equations, Newton's second law, we can do variable substitution, since we have this stiff driveline where we have a direct connection between the torques and a direct connection between the angular velocities, and we can get the tractive force to be expressed like this, and we can develop the following final equation for the vehicle motion equation. So we have the angular velocity here are the mass of the vehicle plus the inertias of the engine and the wheel. So these will gather up as an effective mass that will oppose the acceleration or deceleration of the vehicle. And then we have the components here. We have the torque that comes from the engine that drives the vehicle forward, and then we have the lossless air drag, rolling resistance, gravitational, and the disturbance. We will not use the disturbance force actively in this course. It's there to illustrate that we can have wind disturbances and other things influencing the behavior of the vehicle. When we look at the vehicle motion equation, we have some operating modes depending on what we're doing with the tractive force. Are we pulling the vehicle forward, or are we braking, or are we coasting? In the case of coasting, we can set up a differential equation. So we set this force to 0, and then we get the differential equation that gets this shape, and that can be solved analytically to get this equation here. If we start at a certain velocity, for example 100 kilometers an hour, then with time, as time evolves, the vehicle velocity will decrease and it will reach 0 velocity after finite time. This is an example of how this equation can be used. Another example will come in a few slides. In the hand-in exercises, it will be important whether or not we're working in traction. Then we wonder, how can we determine if the profile requires traction or if it requires braking or coasting? So the traction condition has these, as we discussed on the previous slide. One way to use it is to use the profile to evaluate whether or not a profile requires coasting or traction, or whether it requires braking. To illustrate method number 1 here, we will use the following simplified sketch, where we have a speed profile over time. So we have velocity, and we are standing at this point. Then later the profile has some points that we should pass through. When we're standing at this point, we're wondering, will we need to use propulsion to go from this point to that point? By using the coasting profile that comes here, we can start at this point, and then we evaluate with the coasting profile. It's v coast as function of t. That started here with v0, and then to determine whether or not the profile needs propulsion or if we need braking while we follow the profile, we can compare the end velocities at this point here. If the end velocity is higher than the coast, that means that we need propulsion. If the profile would have been like this, that means that we need to use braking. So this illustrates how we can use the coasting solution. The other method to determine whether or not we require traction is to directly use the vehicle motion equation and insert the profile. For example, for the velocity profile, we insert the derivative of the velocity profile, and here we have the air drag, we have the rolling resistance, we have the gravitational component. So we insert these components and evaluate this equation to see whether or not this f will be greater than 0 or not. So if it's greater than 0, then we need to have traction. How do these kind of profiles look like? We'll look at 3 different profiles in the coming slides. We have the American driving profile, the FTP75, which is the old American profile. For different times, starting from the starting point, we go over time and then we specify a velocity that we need to. Driving profiles in general, first we use for pollutant control, but now they're also using to specify fuel consumption when you certify the vehicle in terms of fuel economy and what class the car will belong to in terms of the environmental classes. One important part is that different cycles would have different energy demands. When we look at the American that we have here, we can look at the European driving cycle, where we have one part that is a city part, easy European city cycle. We have a slow start on 1 gear, where we go only on gear number 1 on this acceleration, then we brake and then we go down here. And we take the next one where we go up to 2nd gear, and then we take this one where we go up to 3rd gear. And this part is repeated 4 times until we come to the highway driving. So you can see that this is city driving and then this becomes highway driving. And here we're gearing up from gear number 1, etc. up to 4th gear, and then when we go up here on the full speed we go up to 5th gear. In this profile there is no coasting, but we see that we have a deceleration here where there is no demand for traction, as the same thing goes here. There's no demand for tractions in these decelerations, as there is no demands for tractive forces here either in all the other decelerations. So this was the European cycle that you will work a lot with during the course here. There's another European cycle that comes from the Worldwide Harmonized Light Vehicles Test Cycle that has been adopted now for Europe and is also being adopted all over the world with some modifications. It has the same behavior as all cycles, that we have a velocity specification over time, and this gun is more demanding than the NEDC, and it has much more transients than the NEDC that we looked at previously. Now we have all the information about the driving cycles. Now we look at what is the energy demand that these cycles require. And to do that we look at the energy demand, so we integrate here. So we integrate the work, which becomes the energy that we're demanding, and then we divide with the total distance. So this is force integrated over distance, so this is mechanical work. So this is the work requirement of the cycle. And here you see the traction condition. We are requesting that we must be in traction. This integral change identify all times when we are in traction. And we can do this change of variables so that we can go from distance over to velocity and integrate over time instead. So here we have the power integrated over time, while here we have force integrated over distance. And both of them end up in an energy requirement. And we're only interested in the traction part. We're not interested in the other parts because they are not a demand of the cycle. So we're only looking at what is the minimum energy requirement that the cycle poses for the vehicle. So the main thing that we'll look at now is to solve this integral. So we're interested in evaluating this integral for various cycles, and that will be one of your tasks here. So how can we work with the cycle? Well, at a certain time t we have a certain velocity, and over the index, if we assume that each time step is separated by time step length h, we can couple the index to certain points in time over the profile. And when we work with this, we're interested in the average velocity because the velocity controls the air drag and it controls the rolling resistance. And we are also interested in the acceleration because that's what we have as a requirement in the vehicle motion equation. So we have velocity and we have acceleration, and we are approximating them over each interval. And the traction approximation then, when we do this, we are assuming that dt is h, so between each sample we have a time step h, so that this integral with the numerical approximation becomes this sum. This is the core of hand-in assignment number 1, where you will work with this sum. You will evaluate this component. So you will evaluate the tractive force, you will evaluate the profile speed, etc. An important part in evaluating that sum is that you need to calculate the tractive force, which is depending on the air drag component. Here we have the rolling resistance, and here we have the acceleration. So we insert the equations that we have on the previous slide into this and rework the sums. So we extract the things that doesn't depend on the velocity profile, like the components of the air drag, the components of the rolling resistance, etc. They don't depend on the summation index. They are constants over the cycle, while velocity and acceleration changes. So here we have air drag, here we have rolling resistance, and here we have the inertia effect. So this is Newton's second law that appears here. When we have acceleration, we need to overcome that, and that requires extra tractive force, while when we have deceleration, we can use that extra tractive force from the inertia effect to overcome the losses. In these sums here, we're summing over the points where we have traction. So you will have to identify where there is traction in the cycle. That's why we looked at the methods some slides ago. So you will combine that identification together with evaluation of these components for all the different cycles and get energy consumption numbers that are the minimum energy requirement for a given cycle. And if we look at these components here over the cycle, we see that the air drag gets these numbers, we get the rolling resistance these numbers, and the mass effect gets these numbers. So now when we have these numbers, it is good to understand what goes on. Are these reasonable? So we look at the full cycle. This number represents the city cycle, and this number represents the highway part. When we sit and look at the results, the next question: do these represent common sense? Can we understand why the numbers are high or low for certain driving? So for example, if we look at the European city cycle, we have a lot of accelerations and decelerations, accelerations, decelerations. So the inertia effect should be biggest for the European city cycle. And that's the case with the highway driving. There's few acceleration, but there's a lot of distance that we're doing at high speed at constant speeds, so that's also smallest. And if we look at the air drag, we know that air drag is most dominating for high velocities. If we look at the city cycle, we have low velocities, so it should be low as it is. And when we look at the highway driving, we have high velocities, and therefore the air drag should be high there. Driving cycles are thus mapped onto different numbers here, and these different numbers reflect, for example, how much high velocity, low velocity do we have by high and low numbers, and how much acceleration and deceleration do we have by high or low numbers here. So different type of cycles will result in different numbers here. These numbers for a given cycle can be put into an equation by adopting the appropriate units and packaging the results, so we can get we collect the coefficient for the design parameters, cross-section area, the drag coefficient. So this is aerodynamic design. We have here rolling resistance design, and here we have vehicle weight related to the acceleration, deceleration. So this equation is then a reflection of these, but just changed so that we get kilojoules per 100 kilometers. And we can use the cross-section area here in square meters and other components. So these constants are encapsulating the changes of units so that we can get a simple equation relating the fuel consumption to these design variables. This is a task in your hand assignment, so you shall do these calculations and get acquainted with the minimum energy numbers. And now when we have this minimum energy number, you could also relate this to what would be the lowest theoretical fuel consumption that you could get for this type of driving cycle, under the condition that you say that you have a perfect powertrain, so a perfect engine, perfect electric machine. This gives you the information of the lowest possible energy need that you have for a certain given driving. If we look at approximate car data, just to give you numbers that you can work with and do hand calculations. So this equation is ready for doing hand calculations, and you can insert if we have an SUV, if it's a full-size vehicle, if it's a compact, or if it's a lightweight vehicle, or the specific car for the Shell Eco Marathon that I showed on the first lecture. You can see that over the European cycle it requires a certain average power, and the accelerations and high speed require a certain maximum power that we need to fulfill the driving cycle as it's stipulated. So these numbers you can return to and you can use for your own calculations if you're interested in seeing the required energy needed for certain driving. At this point we have now arrived where we have an analysis tool where we can look at the driving and altitude profile, and we can back this kind of information up to the cut at the wheels here. So we know what the vehicle will consume if we are given with this driving mission. So you have to fulfill this driving mission. What will be the energy demand of this certain vehicle? At this time I think it's good if we once again make a break and you go and refresh yourself a little bit and get ready for the next. So take, for example, 15-minute break to rest your head and ears and eyes, and get back to the next part where we look at the energy demand and we look at modeling of the system.